Hello everyone. Welcome to the next lab of ECE573 Advanced Embedded Logic Design. So in this lab, we are going to discuss the vivado based flow for programming the embedded system consist of the processor and the FPGA. As discussed in the previous video, here we can't use the ARM processor because ARM processor ELF file is stored in the off-chip DDR memory, and the fetch instruction fetch occurs from the off-chip memory. And for emulating the same, we need to use the SDSoC. So instead of using the ARM processor, we are going to use the soft processor, which is the Microblaze. And in case of the Microblaze, the instructions are stored using the memory created by the block RAM. Okay, so we'll start with the create project. So inside the create project, we'll create a new vivado project. So click on next. So make sure that all this address doesn't contain any space. So this is lab 9 Microblaze 1. Okay, so click on next. Next, here you can select any board. I'm going to select the zedboard. Microblaze can be it can be implemented even on the normal FPGA board. So you can use the Basis 7 or any RTX 7 board. But I'm going to select the Z board because this is the board which we are using for the entire semester. Again, for this lab, we don't need a board access. We are going to do the simulation, so we don't need the access to the board. So that's why you can select any board you want. So as we discussed in the SDSoC, your entire block diagram was generated automatically by your SDSoC tool based upon the files given by you. In case of the vivado based flow, you are going to generate your own block diagram. So what I'm going to do, I'm going to create a block diagram. Okay, so yeah, 9. So create new, create block design. Click on the create block design. So you can see that the zedboard is selected here. Make sure this address doesn't contain any space. Okay, so once your tab is open, click on the add IP, that is plus sign, and select the Microblaze. You can see here you can also do the select the ARM processor via Zynq. But again, as I told you, Zynq simulation is not possible because of the off-chip memory. So we are going to do the same process using the Microblaze. Again, the process for the Zynq and Microblaze is exactly same. So whatever we do today, you can replicate for the Zynq based SoC with the ARM processor whenever you have the access to the board. So first is the click on the run block automation so that you can do the configuration as per your application requirement. For example, I'm going to select some local memory of 32 kilobyte. I am not going to use any cache memories, and all rest of the things will remain the same. And clock, I'm going to add it as an external source so that I can drive this clock signal from my test bench. Okay, so I have done the run block automation, and you will see that there is some complex looking block diagram will be created after this automation is completed. Click on the regenerate layout so that block diagram looks good. So this is your Microblaze. This is your memory of the Microblaze where your data and the ELF file like assembly language code will be, all the instructions will be stored. This is the reset system of the processor. So basically this generate the reset for the different part of the system, whether they are interconnect, whether they are peripherals, whether they are other data processing blocks or the control blocks. Okay, so once you complete this one, then what we are going to do is that we are making the external this signal as a external signal, okay, or we can do the run connection automation, and this we are making it as a active low signal. Active low signal means when this signal is low, then the reset circuit will be in the reset state. When this signal is high, the circuit is in the out of the reset state. I'm going to change the name. I'm going to write reset, and this also I'm going to write it as a clock. So once you are done this, then what I'm going to do, I'm adding the GPIO IP, so general purpose input output IP. So what I'm going to do, I'm in the real world, I'm going to connect this GPIO to the LED, and I'm going to display some numbers on the LED. But we are doing the simulation, so we are going to show you the output of this GPIO. So when I want to write something on the LEDs from the processor, what I'm going to do, I'm going to use say printf statement or something, and that printf statement is passed to the driver, and this driver is converts that into the AXI transaction. Via AXI write transaction, the data is passed to the IP, and that IP extracts the written data and then displays on the LED. So to accomplish this task, you can create your own IP using the HLS, which we will do it in the subsequent lab. But right now, what I'm going to do, I'm going to use the existing IP. So this is the AXI GPIO IP, which means it has the input of the AXI port, and the output is the general purpose input output port, which can be connected to the LEDs or any port. So what I'm going to do, I'm going to do some configuration on this one. So basically, I'm going to use this port only as an output port. So this IP can be used as an input IP, so that when you want to take the data from the switches and push button, you take this IP as an input IP. When you want to send the data to the LEDs, you can take this IP as an output IP. So right now I'll use the all IP as output IP. I'm going to use only 4 bits. That means my board contains only 4 LED. So I'll use the 4 one. If you want 8, you can go up to 32 also. In this IP, there are 2 channels. So on one channels, you can receive the data. On another channels, you can transmit the data. Like you can connect to the one channel is to switch, and another channel you can connect to the LED. Or you can connect both the channels as the output input channel, whether you take the data from the push button and the switches, or both can be the output channel. You can connect to the different types of LEDs or the display. So here I'm going to use only one channel, and I'm going to use the 4 bits only. Okay, so I click on OK. So now if you see in the GPIO, this is the 4-bit only. Okay, and the input is the AXI port. Then run connection automation. I'm going to connect this AXI port to the interconnect wire to, and then to the Microblaze, and Microblaze will act as a master to this GPIO, because Microblaze is going to write into the GPIO. So Microblaze will act as a master. So just click on OK, and now you can see that the this IP is connected to the AXI port of the Microblaze. So this is the AXI data port of the Microblaze. Via AXI interconnect, you can see that this IP is connected to this one. So you can see that from this port, Microblaze will generate the AXI transaction. This will be passed to the this Microblaze IP, and from Microblaze IP, from the Microblaze IP, it will be passed to the AXI interconnect, and from the AXI interconnect, you can see that this is passed to the GPIO. And inside the GPIO, the whatever the data is written, that W data signal is extracted, and then it will be passed out of those 4 LSB bits are passed to this signal. So what I'll do, I'll make this as a external. So that means I can see this signal is in the test bench. Okay. So from the test bench, I'll drive this to signal, and I'll see this signal in the test bench, and then I'll have my C file running on the Microblaze processor. So I'll change the name. I'll say GPIO 4 bits. Okay, so this is the simple block diagram which we have created. So what our system has, we have the Microblaze, we have the local memory to store the code on the Microblaze, code to be executed by the Microblaze, and then we have the GPIO. And what we want to do, we want to write something on the GPIO from the Microblaze. Okay, So first thing is to verify that this block diagram is correct or not. So click on the validate design, and then you can see that the validation is successful. Now let's see the address editor. In the address editor, you can see that you have the from Microblaze, you can see that there are two types of data you can access. One is the regular data and second is the instruction. Instructions are stored in the local memory, and the address local memory we have selected as 32 kilobyte, and the address is starting address is this one. For the data, again, you have the either local memory, which is same as the instruction memory, or you can have the GPIO, and the GPIO address, start address is this one, and the internal memory of the GPIO, whoever has designed this IP, is 64 kilobyte. Once you know the start address and the memory range, you know how to find out the high address. Okay, so these addresses are important because when you are going to write a code, you are going to write and read from, when you are going to write into the GPIO, you are going to write at the particular address of the GPIO. So that's why this address, knowing this address is important. Now coming back to your block diagram. So we have validated the block diagram. Then we are going to create, go to the block diagram and right click and create a HDL wrapper. So this wrapper will create the top file where the clock and reset are input and the GPIO 4 bit is a output. So this wrapper file, Verilog wrapper file, will be automatically created via in this vivado. Okay, so you will see in the source tab, you will see that this file will be automatically created. So you can see that this is my wrapper file. In the wrapper file, you can see that I have the clock, GPIO, and reset are my signal, and you can see that then I am calling this module, and this module is this is nothing but the Verilog module instantiation, and inside this module you will have the all other blocks implemented inside this module. So GPIO Verilog code, interconnect Verilog code, VRAM local memory, Microblaze code, everything is there inside this module. So if you want to look at this one, you can always have a look at this all the corresponding files. Okay, so once you are done with the wrapper, then the last thing you need to do is that you need to convert this Verilog code to the netlist, synthesis netlist. Okay, so now I have converted to convert this Verilog code to the netlist. I need to create or click on the block diagram, right click it, and click on the generate output product. Once you click on the generate output product, you will see that it will do the synthesize the each block of your design. Click on generate. It will take a few minutes to synthesize all the blocks. Depending upon the speed of your laptop, it may take up to 5 to 10 minutes. Okay, so once the synthesis is complete, then we'll see what are the subsequent steps. So I'm going to pause the video and I'll come back when the synthesis is done. Okay, so the process is complete now, and you can see that all the blocks or the synthesis is completed. So the now next step is to export these details to the SDK so that we can generate a board support package, as we discussed in the Zynq boot lab, that we need to first create a board support package, and then using the board support package, we'll write a application code. So I'm going to export the design. I'm not going to include the bitstream because we have not generated the bitstream. We are limiting ourselves to the simulation. So I have exported the design, and then I'm going to launch the SDK. So now the SDK will be launched, and in the using the SDK, we'll write a C code for our Microblaze processor, which will be converted into the corresponding ELF file. Okay, so now in the SDK, you will see the HDF file where you can see that the address map for the Microblaze processor, you can see that there are two peripherals. One is your local memory and the GPIO, and corresponding base addresses and the end addresses are given here. Then you will have for the GPIO IP, you will have the different registers. For example, in case of the GPIO IP to use as an output, you are going to write your data at the particular register inside the IP, and that data will be passed to the LED. So for similarly, whenever you are going to receive the data from the switches, The data from the switches will be stored into the particular register inside the IP, and using the AXI read transaction, you are going to read that data. So from which location you want to read, from which address you want to read, the corresponding details are given here. So you can see that for the channel 1, this is the register address where you can read the data, and you can see it's a 4 total size is the 4 bits. Okay, in the maximum it can go up to 32 bits, that is 4 bytes. Okay, but we are going to use only 4 bits because our LED, we are assumed that our it is only of 4 LEDs. Similarly, channel 2 we have, then for some additional registers are there for the interrupt. So we'll use it when we are going to use the interrupts inside the GPIO. Okay, so now next step is to create application project for the Microblaze. So in this one, I'll again give some name to the project. Then you can see that I'm going to use the platform which I have generated in the vivado, which I have exported now. My OS is standalone. I'm going to use the Microblaze processor. I'm going to write the C code, and then based upon the this platform, I'm going to generate the board support package. And I'm going to use the empty application here because I'm going to write the C code on my own. So once you click on finish, you will see that the corresponding 2 folders are generated. One is your project folder and one is your board support package folder. In the board support package folder, all the details necessary for the hardware communications are there. For example, in the library source, you can see the GPIO, and inside the GPIO folder, you have all the drivers necessary to communicate with the GPIO. For example, in this xgpio.h file, you can see that you have the all the functions drivers necessary to initialize your GPIO, make it as an input or output. You can define the direction of that GPIO. You can write to that GPIO and you can read that GPIO. So whenever you want to write to the GPIO, you will use this function, and this function will in turn will generate the AXI transaction. So for every IP you will use in the hardware, there will be such files are generated along with the driver function, which will help you to communicate with the corresponding IP. And what are these driver functions? These are nothing but they perform the writing to the particular register or reading to the particular register. For example, if you look at this write file, it is nothing but it is performing some write operation to the particular address via AXI transaction. Okay, so these drivers are nothing but they usually communicate with the IP. They write into the particular register in the IP, or read from the particular register to the IP, or change the values of the particular register in the IP. Okay, so similarly for the interrupts, you can see that there are enabling the interrupt, disabling the interrupts. There is a proper procedure are there, clearing the interrupt. We will see it when we are going to use the interrupt. So you need to write a C code using these driver functions. Like in case of the SDSoC, you don't need to worry about this driver function. The linking between your C code and the driver function is taken care automatically. But in the vivado and the SDK based flow, you need to take care of this entire design flow. And you can rest of the files you can have a look at, and you will see the different functionality has been well explained in this file. So there is another .h file is there where all the parameters for these drivers are there. For example, if you see your first register, your first register start with the address 0. This register is 32-bit. So your next register start at this address, which is 4. Then the next register start at address 8 and see. So each register is 32 bits, so address is incremented by 4. Similarly, there are these addresses for the interrupts are there. So you can see that there are so many registers are being used. Then similarly, the mask for the interrupts and all those things are there for channel 1 interrupt, say channel 2 interrupt. So we'll look into those one as and when we need it. Okay. So In addition to this, as we discussed in the SDSoC, we have this XParameterH file. And in XParameterH file has all the details related to the addresses and all the internal calls in Microblaze are there. For example, in this one, you can go to the GPIO and you can see that all the details about the GPIO is there, like what is the start address, end address, device IDs, interrupt is present or not. Right now, interrupt is not present. Whether you are using the two channels, no. So all the details are there, and you need to make use of these details in your C code. Okay. Similarly, for the different IOs, all the details are there. For example, if you have the different type of memory, you can use the, or any other input output, you can use the code inside this to communicate with those IOs. Similarly, for cache memory, cache, you have different functions are there. You can see that the eCache invalidation, different L1, L2 cache invalidation is there. Then there will be a cache for the flushing of the cache. So all the functions are there. Only thing is you need to understand how to make use of this. There should be some function for the DMA. I don't see it now, but there will be some function for the similar function for the DMAs are also there. Okay, this one is for the block RAM. So how to communicate with the block RAM, all those things are there inside this one. Okay, so basically you need to look at all these files, and based upon your application requirement, you need to make use of these codes. Okay, so now we need to write an application. Okay, so in the source file, we are going to create an additional source file. In this one, I'll just write lab9 mb1.c. Okay, we are going to create a C project, so I'll use the C. And what I'm going to do, I'm going to display some value on the LED. Okay, so first I'm going to include the all the data.h file. Okay, so hash include xgpio.h and hash include XParameterH. Okay, and our main function, which will be the first one to be executed in your ELF file. And what I'm going to do, I'm going to display some data on my GPIO. Now, first thing I need to do is that I need to first do the initialization of the GPIO, and for that I need to use this function, and for that I need this structure. Okay, this structure is defined here. So I'll create my local variable of this structure. Okay, so xgpio, say LED GPIO. Okay, so I'm going to create a structure. Then what I'm going to do, I'm going to use this one, xgpio initialize, and the first thing is the address of the structure, and the second thing is the device ID, which device I want to initialize. So if you look at the XParameterH, I need to copy this device ID of my GPIO. So I'll copy this value and then I'll store it, I'll copy it here. Okay, so what I'm saying, initialize this GPIO which I have in my hardware, and copy all the details of the GPIO in this variable. And what is this details are there? Okay, so what I'll get the details, I get the details about the base address. So you can see GPIO base address, then whether the initialization is completed or not, that is the status, whether the interrupt is present, and whether I have the using the two channels or one channel. Okay, after I do the initialization. So what happens in the initialization, you can go here And you can see that what is happening here. Basically, what is happening here is that I am going to check I'm going to call this additional function where I'm going to take the configuration information of this IP. I'm going to read the configuration information from this IP, okay, and then based upon this configuration information, I'm going to complete the initialization. So we'll look into those details for our own IP in the subsequent lab. Okay. So I have in my C code, I have done the configuration, my initialization of my IP. In addition, if you look at here, I also need to set the direction, whether it's an input or output. In our case, it's an output because we are going to display it on LED. So by default, it's output. So we don't need to use this function, but you can always use this function. Okay. And here you need to specify the direction mask. And for example, if you go to this function, okay, you need to specify the direction mask, and that direction mask will be written inside the particular register in the IP. Okay. So then that IP knows that this whatever the data will be coming on this channel will be written to the output port. Okay. By default, you can see that this should be the output IP. Okay. So then we don't need to do that. Then what I'm going to do, I'm going to write a while one loop. So this loop will be infinitely executed, and I'm going to write into the IP. So you can see I'm going to use the discrete write function. You need to provide your structure, GPIO structure, which channel and what data to be written. Okay, so discrete write. Okay, so I'm going to provide the structure, then channel first. I'm going to display the first. Then what I'll be doing after some time, I'm going to display say 2. Okay, then I'm going to display 4. It is some random sequence. Okay, and then I'm going to display 7. I can display 8 because it's a 4-bit, and then I'll go back to 1, 2, 4, 8, and so on. Okay, so what will happen? Microblaze will continuously write the values 1, 2, 4, 8, 1, 2, 4, 8, and so on. After I save this file, you can see that the ELF file is generated, and this file will be used for the simulation. Now, if you go into the debug folder, okay, if you look at the debug folder, if you look at the ELF file, you will see that the ELF file is nothing but the set of the assembly language instructions which are written one after the another. So for every part of your code in your C code, there will be a set of assembly language instructions. So for example, to write the 1, you have the set of instruction. To initialize, you have some set of instruction. Then to write 1, 2, 4, 8 values, you have some set of instruction. Then for discrete write function, you have the set of assembly language instruction. So your code, when your code is now converted into the set of assembly language instruction, and this instruction needs to be stored in the local memory of your Microblaze, and then once we run the simulation, Microblaze will start executing this instruction. So to enable the same, what we are going to do, okay, first thing is that I will go back to our block diagram, and we can see that we need to do 2 things. The first thing we need to do is that we need to write a small test bench, and this test bench will make sure that the appropriate reset clock signals are generated, because we need to drive this signal, clock and reset. If the clock and resets are not generated, your Microblaze will not work. So we need to generate this clock and reset signal using the test bench. And the second thing we need to do is that we need to link this Microblaze processor with the ELF file which we have written. Okay, so that is the next 2 steps we need to do, followed by the simulation. Okay, so first thing we'll do is to add the test bench. Okay, so to add the test bench, what we are going to do is that click on add source, create a simulation source, then create file, lab 9, Microblaze 1, test bench. Okay, so the Verilog file will be created. This will be the empty Verilog file. And inside this test bench, we need to instantiate our this entire block diagram. So we are going to this wrapper function. We are going to copy this definition of this wrapper function, and inside the test bench, which is empty one right now, we are going to do the instantiation. Okay, so this is our module. This is our DUT. Then I'm going to use the named instantiation. Okay, instead of the order instantiation, I always prefer the name one. Okay, so all the signals which are input to our DUT will be defined as a register, and all the output of the DUT will be defined as a wire. So 3 down to 0, and this is the GPIO 4 bits. Okay, then the next thing is to initialize all the register, which is clock is equal to 0, reset is equal to 0. So initially is the active low reset. After say 100 times time unit, I'll make it as 1 so that my processor will come out of the reset. And the last thing is to generate the clock. Okay, because I need to drive the clock to the processor, otherwise it won't work. Okay, so we have written the small test bench where we are just driving the clock and the reset signal. Okay, so now you can see that inside your test bench, your block diagram is there. Okay, in the one below your test bench. Now we have completed the test bench part, and now the second part is the how to associate your ELF file to this processor. So to do this, go to your block diagram. Okay, right click. In this one, you can see that there is a option called associate ELF file. In the associate ELF file, you just need to click on the simulation sources, the corresponding ELF file, and select your ELF file. So your ELF file will be there in your project folder. Go to the SDK folder. Inside the SDK, your SDK project. Then there is a debug project, and there you will see the ELF file. Click on OK. Now you can see that in your simulation, you are linking your ELF file to your processor. Click on OK. Okay. So now you have linked the ELF file to your processor, so that this ELF file, the set of instructions are stored in the memory. So when you start the simulation, once the processor receives the clock, he will read the instruction from the local memory and start executing it. Okay. So the final step is to run the simulation. So I'll click on the run simulation and then click on the run behavioral simulation. Okay, so you will see the simulation window like this, and if you see that, if you run see the simulation waveform, you will see that the nothing has happened. Okay, your GPIO is 0. This is because the processor has not completed the initialization stage, and processor has not reached the corresponding while one loop. So to do this, what you need to do, you need to run the simulation slightly more time. Okay. So let's see that we'll run the simulation for 2 microseconds more. Okay. So we'll run it for 2 microseconds and we'll hope that something might happen. Okay, nothing yet happened. Let's run for the 2 more microseconds. Yeah, so something has starting to happen. And so let's run for 2 more microseconds. And you can see that your 1248 your code has started working. You are in the while one loop. Okay, so that's why we have completed the first step. We have done the simulation of the Microblaze processor. Now we need to understand how the signals are transmitted from the Microblaze to the your IP. Okay, so the first thing is that how the Microblaze reads the instruction. Okay, so if you go here, you can see that the Microblaze IP is communicating with the your memory, local memory, and this local memory, you can see that the there should be some instruction address, and then there should be some instruction coming. Okay, and then there is this fetch signal. So let's add this signal to the waveform. Okay, right now these signals are not captured, so you won't see those. So let's run the code for 2 more microseconds and you will see the corresponding instruction. Okay, so you can see that the some signals are being added. So let's zoom it, and what you can see here is the, you can see that the instructions are being fetched from the particular location, and then from the particular location inside the memory. So let's start with the time when you start printing the 1. Okay, so you can see that you start the fetching the instruction, and you are fetching the instruction from 6D0. Okay, let's go to the ELF file and look at the 6D0, and you can see 6D0 is when you write 2. Okay, and if you see here, you have already written the on the GPIO 1. So next thing you are going to write is the 2. Okay, so you can see from here you have already written the 1. Now you are doing all these instruction. You are going to execute all the subsequent instruction to write the 2. Okay, so once you execute all this instruction, you can see that the data is 2 is written on the corresponding GPIO. So let's go back to the instruction. You can see is 6D0, then 6D4, 6D8, and if you go here, you can see that these are the instruction. Then after 6E8, okay, after 6E8, you go to the 6EC, okay, 6EC, okay. So that means you start executing the next set of instruction. So now you can see that from 6D0 you have read this instruction, which is the 30E, okay, 30E0002. Okay, so you can see there is a 1 clock cycle, and you can see that you execute up to this instruction, okay, 8 all 0. So you can see that you will execute up to this instruction, and then you can see that there is a sudden jump. And why this is happening, you can see that there is a branch instruction. Okay, there is a branch instruction. What is this branch instruction? This is nothing but the to the 794 and this one. Whenever the branch instruction happens, you need to flush your pipelining and you go to the, so that means whatever the instruction you have fetch or decoded, you need to ignore them, and then you go to the 794. And if you go to the 794, this is nothing but the discrete write. Okay, And every time you can see that in every case you will go to the 794, and at 794 you execute the discrete write instruction, which has the if you go to the 794, you are going to execute all these instruction, and based upon after you complete this instruction, your discrete write will be completed, and then you will go from 1, you will go to the 2. Okay, this is how you can see that how the instruction fetch and the decoding happen, and we have also seen the example of the branching and when your pipeline needs to be flushed. Okay, so this is about the instruction. Second thing is about the how the data, these instructions are converted into the AXI transaction. So to go to the block diagram, we can see in the block diagram what happens. Your code which will be executed, you are displaying the data on the GPIO. That means on the DP port you are generating the AXI transaction. Okay, so if you go to the simulation again, let's go to the GP port of the DP port of the Microblaze. So you can see that DP port of the Microblaze. I am interested in the right channel, so I'll take the AW signal. This one, all the AW signal I am going to take. Okay, so I'll just select all this signal. I'm going to add to the wave window. And if you look at this DP signal, okay, you can see now, if I zoom out, you can see that at the regular interval, this is the starting address. This is my first register, data register. I am doing the write operation and I'm writing the particular value. So here you can see that all these instructions were to write the 0. So I have created the 0 here, and then this 02 is displayed on the GPIO here. Okay, so I have written the 02 via DP port. I have generated the AXI write transaction, and that is displayed on the GPIO. And this, you can see that at the regular interval, this process will continue. I'm just converting this into the unsigned integer, so it is visible. So you can see I'm writing 1, 2. After 2, it will be a 4. After 4, it will be a 8, and this process will keep on repeating. Okay, so this is how the AXI transactions will be converted from your instructions are converted into the AXI transaction. We have seen signal here. You can see the signal here. You can see the signal here by looking at the appropriate signals of the GPIO or this AXI interconnect. Okay, so this completes the basic lab of Microblaze simulation, and now you can see that you are getting the more understanding about the how the drivers and how the communication happens between the processor and your peripherals. Only difference here is that instead of using the ARM processor, we are using the Microblaze processor, but the exact process will be same for the Microblaze ARM processor only. But the problem with the ARM processor is that your ELF file is stored into the DDR memory, which is the off-chip memory, and that's why you can't do the simulation inside the vivado. Okay, so that's why we have replaced the ARM processor with the Microblaze processor.